Very good morning to you, student. Today I am going to discuss with you one more theorem related to uniformly continuous function. So this theorem states that a function which is uniformly continuous on an interval I, on an interval or any interval I, will always be continuous on that same interval, which means that uniformly continuous always implies continuous. Uniformly continuity always implies continuity, whereas the converse need not be true. And the example for that is the one that I gave you. F of x is equal to 1 by x defined in an open interval 0, 1, where the function is continuous at that point, at that interval, but it is not uniformly continuous. So how we state this theorem? What is the given condition is that f is uniformly continuous on an interval I. So if f is uniformly continuous on interval I, so for a given epsilon, by definition of uniformly continuous continuity, there exists, for every epsilon greater than 0, there exists a positive number delta such that mod fx1 minus f of x2 is less than epsilon whenever mod x1 minus x2 is less than delta for all x1, x2 belong to I, which means that this delta depends on epsilon. At whatever points you take in this interval I, f mod fx1 minus fx2 is always less than epsilon whenever mod x1 minus x2 is less than delta. Now you take this x1, let us take x to belong to be any point in this interval I. And by taking x here in particular to be equal to x1, we find that mod f of x, or here it should be f of x only, mod f of x minus f of x2 is less than epsilon whenever you just replace x1 by x only. So we have mod fx minus f of x2 is less than epsilon whenever mod x minus x2 is less than delta. So this implies that f is continuous at the point x2. So if it is continuous at the point x2, because this is true for all x2 is any arbitrary point of I, so this implies that f is continuous at that interval I. So thus we have shown here that if a function f is uniformly continuous, it always implies that it is continuous on that interval, whereas the converse need not be true. You can consider this example here. However, the converse is not true. For example, let fx equal to 1 upon x defined in an open interval 0, 1. Clearly, f of x is continuous in this open interval, but not uniformly continuous. Okay, let us see one more example regarding this uniformly continuous function in a closed interval minus 1, 1, let f be defined as f of x is equal to x squared into sine of 1 by x when x is different from 0, and it is called 0 when x is equal to 0. In the given interval, is the function bounded? First, the question is that this is an annual exam question which came forgot the year. Okay, so in this interval, they ask the first question: is this function bounded? Is it continuous? Is it uniformly continuous? So what we have to show is that to show that it is bounded, first let us see that whether it is continuous or not. So once it is continuous, then we can answer the first and the third question. So you are given f of x here is equal to x squared into sine 1 by x squared when x is different from 0 and 0. So to check for continuity, let epsilon greater than 0 be given, then there exists a delta such that at the point 0, okay, we have to check the continuity because it is defined when x is different from 0, f of x is x squared sine 1 by x squared, and it is 0 when x is equal to 0. So let epsilon be given, then there exists a delta such that mod fx minus f of 0 is equal to x squared into sine of 1 by x, and f of 0 is equal to 0 minus 0. So what we have here is mod of x squared into sine of 1 by x squared using this product rule of modulus function. So this is same as mod of x squared into mod of 1 by x squared, but the maximum value of mod of sine of 1 by x squared is 1. So this will be less than or equal to mod of x squared whenever mod x minus 0 is less than delta. Now by taking delta equal to root epsilon, we see that mod f of x here will be less than or equal to epsilon. This whole thing will be less than epsilon whenever mod x minus 0 is less than delta. So that is, what is delta we have taken here? Delta is equal to root epsilon, which depends on epsilon. So this implies that f is continuous on closed interval minus 1 1, and because of the first theorem on continuity and uniformly continuous, that is, if a function is continuous on closed interval, then it is always uniformly continuous. So since f is continuous on this closed interval minus 1 1, then this implies that f is uniformly continuous, and moreover it is also bounded, because we have proved what first theorem from continuity is that if it is continuous on closed interval, then it is always bounded. So I'm using to answer question 1 and 3, I'm using this result, that is, if f is continuous on closed interval ab, then it is always bounded. So here, since f is continuous, it implies that it is bounded by this remark, by this star 1. And to check for uniformly continuous, you don't have to prove the result. You just use that statement, that is, if f is continuous, once f is continuous on a closed interval, then it is always uniformly continuous. Now we come to this discontinuous function. A function here, only the types of discontinuity will discuss. There is no theorem, nothing, just the examples I will give here, which satisfy those types of discontinuity. A function which is not continuous at a point C of its domain is called a discontinuous function. So any function which is not continuous is called a discontinuous function, and the point C here is called the point of discontinuity of the function. And there are different types of discontinuity. The first one is called removable discontinuity. So here, what is this type of discontinuity? A function is said to have a removable discontinuity at x equal to c if limit x tends to c. F of x means if limit x tends to c, f of x exists, but it is not equal to f of c. F of c may or may not exist. So such a function is said to have a removable discontinuity. So for example, note that limit x tends to c, limit f x tends to see f of x exists means that both the left hand and the right hand limit must be equal, but it need not be equal to f of c. So you can consider this example. F of x is equal to x squared by 2 at x is x squared by x. This is x at x. Then limit x tends to 0 plus f of x is equal to limit x tends to 0 plus x squared by x, cancel 1x from denominator and numerator, so it remain as x, so is equal to 0. And limit x tends to 0 minus f of x is equal to the same thing, it is equal to 0. As you can see, both the left hand and the right hand limit are equal. But f of 0 is undefined. Why? Because 0 squared by 0 is undefined. So this is an example of a removable discontinuity, means a function where the limit f of x exists, but it need not be equal to f of c. So this type of discontinuity can be removed by assigning a suitable value to f of 0. That is, by assigning f of 0 is equal to 0. So this whole thing will become continuous. Now a function which is said to have a discontinuity of the first kind at x equal to c if limit x tends to c plus f of x and the left hand limit and the right hand limit exist, but they are not equal. So such a function is said to have a discontinuity of the first kind at x equal to c if the left hand and the right hand limit need not be equal. So for example, you define f of x here is equal to x by mod x when x is different from 0, and it is equal to 0 when x is equal to 0. So in this case, we have limit x tends to 0 plus, that is, the right hand limit is equal to limit x tends to 0 plus x by mod x. So when x is greater than 0, we know that mod x is equal to x. So this is x by x, which is equal to 1. Now the left hand limit is x tends to 0 minus to the left of 0. So you have this mod x will be less than 0. So when x is less than 0, mod x will be minus x. So you have x by minus x is equal to minus 1. So you can see both the left hand and the right hand limit exist, but they are not equal. So such a function is said to have a discontinuity of the first kind. Now fx is said to have a discontinuity of the first kind from the left at x equal to c if the left hand limit exists but not be equal to f of c. For example, you define here f of x is equal to 3 when k is less than 0, when x is less than 0, and 1 when x is greater than equal 0. So when x tends to 0 minus, so when x is less than 0, the fx is assigned to 3. But what is f of 0? Because when x is equal to 0, f of x is equal to 1. So the left hand limit exists, but it is not equal to f of 0. Such a function is said to have a discontinuity of the first kind from the left. Similarly, it is called a discontinuity of the first kind from the right if the right hand limit exists, but it is not equal to f of c. So you can see this example. Then one more type of discontinuity is that a function is said to have a discontinuity of the second kind at x equal to c if neither the left hand nor the right hand limit exists. So such a function, any function in which the left hand and the right hand limit does not exist is called a function of this said to have a discontinuity of the second kind. For example, you define this. F of x is equal to 1 if x is rational, and it is equal to 0 when x is an irrational number. Let us check the discontinuity of this function at x equal to 1. So the right hand limit, that is as x tends to 1 plus f of x is equal to 1 if x is rational, as x tends to 1 plus if x 1 plus is an irrational, it will become 0. So they have two different values. So in this case, the right hand limit does not exist. Similarly with the right hand limit also. Now last one, this one, fx is said to have discontinuity of the second kind from the left at x equal to c if the left hand limit does not exist. So you can consider this example. F of x is equal to root x minus 3 plus root x plus 3. Here limit x tends to 3 minus, so this will become minus, so it does not exist because here we define a real value function, but whereas here you will get an imaginary number. So such a function is said to have a discontinuity of the second kind from the left, and it is said to have a discontinuity of the second kind from the right at x equal to c if the right hand limit does not exist. So you just give the example, but just change this x minus 3 to 3 minus x. As you can see here, as x tends to 3 plus this one, this whole thing again will become minus inside the square root, so which is an imaginary number, but since it is a real valued function, so this shows that the right hand limit as x tends to 3 plus does not exist. So these are the types of discontinuity, and the example also I have given you. So if anything is not clear, you just let me know.